Welcome, I'm Terry Soul, and this is Programming Chaos, a channel devoted to fun and interesting programming projects to help you hone your programming skills. Today's project is flow fields. So flow fields are basically an array of vectors representing forces or flows, and from that array of vectors, we can generate very interesting patterns by having lines that follow the vectors, or you can model the motion, for example, of particles through a complicated force field. So lots of fun things that we can do once we have the basics of flow fields down. The standard idea for a flow field is simply we have a grid, and each cell in that grid has a vector pointing in a particular direction. A lot of where we get the interesting variation and beautiful patterns from flow fields is based on how we pick that vector field. To get started, we have to begin, of course, by creating the field. And one of the big decisions to make right off the bat is whether our vectors are going to vary in length or whether they're going to be normalized. It turns out using normalized vectors still gives you quite interesting patterns. That simplifies things even further. If we know the length of the vector is always 1, really all we need is the angle. So although flow fields seem maybe a little complicated, as we get into the coding, you'll see they're kind of straightforward. We just have a two-dimensional array of cells. Could do 3 dimensions as well, but I'm not going to mess with that. And each cell contains the angle that represents the vector. And even before we get quite that far, we should recognize that we've got to decide on the scale of those cells. So having 1 cell per pixel is probably a bit too much. So with that in mind, we can get started. So I'm going to set my scale to 10, which is basically to say each cell is going to be 10 by 10 pixels. And you can make that bigger or smaller, or even I've left room here to make it fractional. So you could say each cell represents half a pixel. Then we need the number of rows and the number of columns that is going to be our array that represents the flow field, and then we can define the flow field itself. So now we've got the basic variables we need, and we just have to give them values. As is typical, I've already sort of done the boilerplate for my processing, my setup and my draw functions. And so now we need to know how many rows and columns we want to use. So the number of rows is simply the height divided by the scale, and the number of columns is the width divided by the scale. And now we can set up our flow field. And our flow field is just an array of that size. Now that we've defined the array, we need to fill it with values. And to do that, I'm going to use a separate function to generate the flow field. And in fact, as I said, we may have many different ways we want to generate our flow field. So I'm going to use a separate function for each one. The first one I'll do is using the built-in processing noise function. So there are lots of different functions to generate different kinds of noise. This is maybe not the best one, the most sophisticated one, but it happens to be the one that's already built in. So of course it's easy to access. So the first thing that you generally need for two-dimensional noise, which is what I have here because I'm filling a two-dimensional array, is a scale. And that's sort of how zoomed in or zoomed out you are on the noise level. And this is a parameter that you should definitely play with to get effects that you want. 0.1 is not a bad place to start, so that's where I'm going to begin. And then we can simply use that to fill in our flow field with random values. So I'm going to be using the map function to fill in the values. Noise gives me a number between 0 and 1, and I need to remap that between 0 and 2 pi because I want my vectors to be able to point in any direction. So there's the map function, and now we use the noise function. So I'm generating the noise here, and that is between 0 and 1. And I'm going to use the map function to map it from 0 to 2 pi. So generate the noise in this range and then map it using our map function into this range. And there we go. Close off our function. And this generates the flow field for us. Now, of course, if we want to do anything with it, we need to be able to see it. So the next thing I'm going to do is put into my draw loop a function to draw the flow field so we can see it. We could draw the flow field directly in the draw loop, but I want some different functions to look at the flow field in different ways. And so just as I have a choice, or will have a choice of different ways to generate the flow field, I want, in a sense, a choice of different functions that will draw it for me. So first we pick our stroke color, and I'll begin with white. So this is actually, if you think about it, a hue of red, but I have 0 saturation because up here I'm using hue, saturation, brightness. So 0 saturation, which will give me white, and 100% brightness, which is why it looks white. And now I simply go through every location in my flow field and draw a vector in the appropriate direction. And it's worth mentioning I have 2 choices here. For each cell, I could go to that location of the cell, use the angle, and use basically the sine and the cosine to figure out where the other end of the line could be. Or, and this is the approach I'm going to take, I could translate to the middle of the cell, rotate by the right amount, and then just draw a line along the x-axis. Both work. I happen to like this approach a little bit better because conceptually it's easier for me. So I begin, as always when we're doing translations and rotations, by pushing the current matrix of transformations onto a stack. I'll do my transformations and rotations, draw my line, and then pop that back off the stack to go back to my old coordinate system. So push the matrix on, translate to the right location, and this is always tricky. When we think about our array, arrays are written as row column, so the row comes first. But the row is what row we're in moving down the screen, which is really the y value. And so always takes a little bit of thought for me. In the array, the row comes first, but when we're drawing, the y value is second. So in a sense, the row comes second. And the column, which is which column we're in, is the equivalent to the x value, so it comes first, even though in the array, columns come second. Always a little tricky, and about half the time I get it wrong and have to fix it. So we've translated to the location that we want in terms of the cell, and then we just rotate by the angle in that cell. Strictly speaking, we may have translated to the upper left corner of the cell, not the middle of the cell, so you could add plus half the scale and plus half the scale. Doesn't matter too much if you do or you don't. I'm not going to bother, but if conceptually that makes a little more sense to you, that's fine to do. Now that we've moved to the cell, we've rotated by the right amount, we just have to draw a line along the x-axis, so that's easy. From the origin, which is now in the cell, and I'm going to make the length of the line for now half of my scale. So if my cells are 10 by 10, I want my line to be 5, for example. And then we can close off those loops. And this is enough to see the basics of the flow field, assuming there's no errors. And there is. You'll notice the error message I get might not be readable. Push matrix cannot use push more than 32 times. I forgot to pop my matrix off. There we go. And so here's our flow field, and you can see what we have is a bunch of little vectors pointing in different directions. And the way they're generated is from our noise, and so there tends to be a pattern. We see clusters where they're facing in mostly the same direction, and then they vary a bit as we go. We can turn up the contrast, so maybe this would look a little better with a black background. There we go. One thing that's worth noting, and again, I'm not going to worry about it, but it's something that you may want to play with, is noise functions typically are pretty heavily centered towards the middle of their range. It ranges from 0 to 1, but they tend to cluster around 50 with sort of a Gaussian distribution. In this case, 50 gets mapped to pi, because that's the middle of our range from 0 to 2 pi. So on average, we're going to have a lot more angles that are pi than the other possibilities. This is one of the things you run into when you're dealing with different ways of generating random noise. For these projects, it's fine, but it is the sort of thing you might want to change later on. What I am going to do is change this scale here. So instead of drawing something that is half the length of the scale, we could try drawing something that is the length of the scale. So I'm just making the lines a little longer, and you can see we get a slightly different looking form here. And then we can go further. Maybe I'll do 3 times the length of the scale. And now we're starting to get sort of a fuzzy looking shape, which is kind of cool. Another thing that's interesting to do here is to change the colors, because these are just sort of all boring lines. They're all white. And there's lots of ways to do that. One effect that I find is interesting, and I have not seen used very often, is to base the color of the line on the direction of the vector. So I'm going to go in, and for my stroke, I'm going to make the hue based on the angle, which is to say the flow field value. That is the angle. So I'll copy that. But again, I need to map it. So I'm mapping the flow field, which ranges from 0 to 2 times pi, and I want to remap that to 0 to 360 because my hues go from 0 to 360. So that's the hue, and then I'll max out my saturation and brightness. And now we get this very colorful effect, and you'll see patterns of color. So all of these lines are sort of in the same direction, and so they get roughly the same hue. And we're starting to get this sort of interesting 3D effect. So right off the bat, we've got a couple of things to play with. The scale of the lines, that is to say the length, and how we handle the color. One of the things that you'll notice here is these are all very broken lines. So you'll see lots of jagged edges, and that's because for each cell, we're drawing a unique line. A much better effect, or a different and in many ways interesting effect, can be obtained by drawing a continuous line that moves from cell to cell. So that's the thing that I would like to do next. So this is my draw flow field, and like I said, we're going to have different ways of representing the flow field. So instead of drawing one, I'm going to call this illustrate. So we need to write this function now. And the idea for illustrating the flow field, if you will, is to start in a given cell, follow that vector, and when you get to the next cell, change the direction of the line to follow the new angle, that is to say, the new vector. And to do this, because we need to draw lines, we're going to need to know sort of the old xy position and a new xy position, so we'll need to start with those variables. And I'm going to have each line start at a random location. That will be the random starting location of my lines. And then I'll just do a do loop and continue drawing them either till we reach some maximum length or we reach the edge of the screen, because there's no point in drawing off the edge of the screen. So I need to add C, and then I also want to keep looping as long as that's less than the number of steps and I'm still on the screen. There we go. And I should put in my counter. And amongst other things, on every loop, I'll increase my counter. So this is going to allow me to draw, in this case, 20 line segments for my line. I have the old point for the current line, and what I need now is to calculate the new xy based on the current vector, the angle in the current cell. So let me grab that, the angle in the current cell, which I get from the flow field. And I get it from the flow field at my current location. And this is what I mean by that. I take the y location that I'm at, divide it by the scale, and that tells me what cell I'm in. And I have to turn that into an integer, and then I do the same thing for the x value. And with that angle, I can now calculate where the next point should be. And for that, I use a little bit of trig. So my new location, my new x location is my old x location plus the cosine of that angle times the scale that I'm dealing with. And my new y is the same thing. It's the scale times the sine of that angle. So that gives me the new x and y, and now I just want to draw a line between them. I'm going to use the same trick I did before and make the color of the line based on the angle. So there we go. The hue depends on the angle, and I'm mapping the angle. Used to be 0 to 2 pi, so I'm again mapping it to 0 to 360. But in this case, I'm going to do the same thing for the saturation and brightness. So the saturation is going to be based on the angle, but of course here I have to map it to 100, which is the maximum saturation I can have. I'll just put this on the next line so it's easier to see. Same thing for the brightness. I'm taking the angle and using that to determine the brightness that I want. And now I can draw my line. And it goes from the old xy to the new xy, and then finally to close the loop, I make it so that the old x and the old y are what are now the new x and the new y, so I can loop around and calculate my next new x and new y. So there's a different way of drawing, or in this case, illustrating the flow field. Let's see how it looks. So we're drawing random lines. It's picking a random starting point and then following the flow field for a little bit. So each of these lines is a line that is following the flow field. And just like with the draw version, I'm getting this interesting sort of 3D effect because the angle determines the color and it also determines to some extent the hue and the brightness. We're not getting as much of a rainbow effect as you might expect because, as I said, most of my angles are really around pi. And you can adjust that if you want by playing around with the map. We can vary this quite a bit by doing things like changing the maximum number of steps that we take. So if I were to make C much smaller, then each of my lines are going to be a lot shorter and it will take more of them to fill in the whole image. We can also get different effects if we go up and change the original scale. Similarly, if I were to lower the noise scale quite a bit, now we're going to see a lot less variation. We sort of get just one continuous movement with a little bit of noise because in a sense we've zoomed in on one region of the noise. Another thing to try are, for example, to change the color depending on the starting location. So if you start near the top of the screen, you get one color, different colors as you move down, which gives you sort of a cool rainbow effect. So now we have two different ways of drawing or generating images from our flow field, but we only have one way to generate the flow field, and that is using our noise. So what I'd like to do is show one example of another way to generate flow fields. And this one, instead of being random, is going to be more of a pattern. So that's what I'll call this function. And I'm going to use it in the place of my old generate flow field. So now I want to generate this patterned flow field. And I'm going to come down and just copy my flow field function because I want to do the same sort of thing. I want to fill in all of the values in the flow field. But this one is going to be a pattern. So I can get rid of the noise scale. And for the flow field itself, instead of using noise, I'm going to use some sines and cosines. I'm going to use a different variable to begin with and then map it into the right range. So first I'll calculate the value and then I'll do the mapping. One is a little bit arbitrary. I'm going to take the row I'm in and take the sine value of that. So as I move down the rows, my angle should sort of vary as if it was sinusoidal. And if we're thinking of it as a vector, my vector will rotate around based on the sine. I'm doing this in terms of radians. So R goes 1, 2, 3, 4, which is pretty large jumps in radians. So that's why I'm multiplying it by 0.1 instead. And I'll do the same sort of thing with the cosine. But in this case, I'll use the column. And I'll change the scale a little bit just to sort of mix things up. And this you can play with all you want. This is the sine plus the cosine, so the maximum value I can get is 2, and the minimum value I can get is -2. And so that tells me how to do my map. I'm going to map from the value, which can range from -2 to 2. I want to remap that to the full range of possible angles, 0 to 2 pi. If I run this, we'll see a very different pattern emerge. I get a lot more variety of colors because unlike the noise, which focuses on 0.5 or about 1 pi, this is more uniformly distributed. And because of the way that I'm doing the shading, you again get some pretty decent 3D effects. This is the illustration. Let me switch back just for a minute to drawing the flow field. And I'm going to turn my scale back down to times 0.05, or excuse me, 0.5, and then we can see the actual vectors. So those are the vectors and the direction they're pointing in, and I left in my draw flow field the maps for the colors. So here we get a pretty cool rainbow pattern effect as well. That should give you lots of different things to try, but there's one more I want to do. If we think about these vectors as forces, we should be able to put some particles down and have them follow the vectors, and then we can watch the particles sort of move through this space. In order to do this, the first thing I have to do is create a particle class, and then I can create a whole bunch of particles. So let's go ahead and do that. So a new tab, so I can create my particle class. And I want each particle to have a position and also a velocity. So the vectors in the flow field will be force vectors that apply a force onto the particles that changes their acceleration and their velocity. And I'll do that position and that velocity as p vectors. And then for my constructor, I'll just put, at least initially, each particle at a random location and initially with 0 velocity. And I'll begin with a display function, which is pretty straightforward. I'll just put a red particle at the position. I'm also going to need an update that actually applies the vectors. But now that I have the class, I can at least go ahead and make a bunch of particles to look at. So let me come back over here to my main code, and I'll do a swarm of particles, and I need a number of them. Maybe start with 100. And now I need to create the individual particles. And now I need to draw them. Could do this as a separate function, but I'll just put it into the draw loop for now. And as long as I'm drawing the particles, I'll get rid of the flow field. There we go. This should work. Let's see. Oh, an extra 4 that I put in. There we go. So not very exciting, but I've got my 100 particles. Now I need to get them to react to the flow field. So for that, I'm going to create an update function. I'm going to sort of stick with the physics. So the first thing I need to know is what is the acceleration due to the force vector at the cell that this particle is in. So I need an acceleration, which will start at 0. And then all of my vectors have a length of 1. They're all normalized. So I might want a scalable force. So I'm going to put in force, but for now I'm just going to make it 1 and leave it as something that you can play with if you want. And so the acceleration then in the x direction is going to be that force times the direction of the angle. And in this case, I have to do it separately as the x and the y, so I need to use my cosine and sine. So for the x, I need the cosine of the angle. So there's the x piece, and this should look familiar. It's almost exactly the same approach that I took when I was doing the illustration. I was sort of drawing the lines by using the cosine of the angle at this particular location. So first we do our x, except of course I have that backwards because here, remember, I'm referring to my 2D array, and that's rho first, and rho is the y value. So this should actually be y. Told you I often get it wrong. And then we need to know the X position, which is what column we're in. And just to add that and go off the edge a little bit, but that's okay. So there we go. Expand this for just a minute. The acceleration in the X direction is the force times the cosine, which is to say the X component of the angle. And then for the acceleration in the Y direction, we just take the same thing, but now it's the Y direction and we then use the sine. So that tells me the acceleration that I want to apply. And so to apply the acceleration, we simply take the velocity. And because I'm dealing with p vectors, I'm using the built-in p vector functions, which in this case is add. So I'll add the acceleration to the velocity and then take my position and add the velocity to my position. And so now the particle's position has been updated. And then the last thing we need to do is make sure that the particle stays on the screen. So I'm going to wrap the X and Y value. So there we go. Add the width and then do a modulus of the width, and that will wrap us in either direction. And the same thing for the height, to wrap off the top or off the bottom. And one more thing that we should do is add, in a sense, a friction. So we should slow down our velocity a little bit. Otherwise, we just keep adding more and more forces and our particles go faster and faster. And so now I'm going to take the velocity, and again, using a built-in vector function, I'm going to multiply it by, I'll do 0.6. This is, again, a sort of how much you slow it down by each time. So this is now our update for the particle. And come back to our main code. Before I display the swarm, I want to update each particle in the swarm. And I have an array out of bounds error. You can maybe see it down here. And the reason for that is I left these as Y when these should be the X values here. So hopefully that fixed the problem. And now we can see our particles moving. And you'll notice they're following the same sort of shapes that we saw before. And so because here I have my patterned flow field, they're following that pattern. And I didn't fill in the background, so let's go ahead and do that. So I'm going to add in a background here. And now you can watch them, and what ends up happening is they tend to fall into a particular part of the pattern, and we do have a little bit of an issue with this pattern with wrapping because it is not symmetric as we go around the edges. What's happening here is they're getting to one edge of the screen and being pushed off it and then being pushed back off the other way because this isn't a symmetric pattern. So we might get a better result if we go back to our noise-based flow field. There we go. And so now they're following that noise. You will tend to see the same thing emerge in that all the particles fall into very similar patterns. So even though they started all randomly, now they're following one of three different particular paths. And that's a very important concept. What's happening here is as soon as two particles, they start in all random locations and they're all following these vectors, but as soon as two of them end up in the same cell, forever after, they're going to be following the same set of vectors. And so this is what you see. Basically, the particles come together in particular sets of patterns. This won't necessarily always happen. It depends a little bit on things like how much friction you're using. If you have less friction, then they have more momentum, and you might have two particles that enter the same cell but with different velocities, and they might end up going in different directions. There is several different things to play with. We have different ways of generating flow fields to get different patterns. We can draw the flow field itself. We can illustrate the flow field, which gives us all sorts of interesting forms to go with. Or using this new idea, we can put particles into our flow field and watch how they move. So the idea of flow fields is a super powerful one used in all sorts of different applications. And here, used in particular for very cool procedural generation effects. So lots of things for you to work with. As always, if you get any really interesting effects, please feel free to put a comment down below. Excellent. Thank you very much.